Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at more examples of implicit differentiation. So in the previous video I introduced implicit differentiation, and we looked at some examples of how to differentiate implicit relationships. I want to continue with that in this video and look at equations that get a little bit more complicated. So remember, we're using our power rule. Anytime we see a y, we think of it like we think of the u in this power rule. So sometimes your functions are going to look like this, where you're going to have products. So remember, we have to use our product rule on this. And our product rule says that we take this first factor, which is x, and multiply by the derivative of the second factor. The derivative of y with respect to x is dy dx. And then we add y, the second factor, times the derivative of the first factor, which is a 1. So remember, when you have a product, a function times a function, in order to find your derivative, you have to use the product rule, which says it's u times v prime plus v times u prime. And you can write them in any order. And then we continue. The derivative of x squared is just 2x. And the derivative of 5y will be 5 times the derivative of y, which is dy dx. So now you want to get all the terms containing dy dx on one side, and choose to move your terms so that you have the fewest number of negatives as possible. So I'm going to move this term to that side. So y plus 2x stays here, and I will have 5 dy dx minus x dy dx. Once you have all your terms containing dy dx on one side, you factor it out. Factor out a dy dx, and we're left with 5 minus x. Now we can isolate dy dx. We're going to divide by this factor. So dy dx will be equal to y plus 2x divided by 5 minus x. Let's take a look at some more. In our next example, we can rewrite these terms so that we're not having to deal with quotient rule. Remember, when your numerator is a constant, you don't need to work with quotient rule. You can rewrite this as 4 times x to the negative 2, and you can rewrite this as 3 times y to the negative 2. And now it's just a constant times a function, so I don't need to use the product rule when it's a constant times a function. I only use the product rule when it's a function times a function. So the derivative here will simply be 4 times the derivative of x to the negative 2, so that would be negative 8. X to the minus 2 minus 1 is negative 3, plus 3 times the derivative of y to the negative 2. This is where I use this rule. So it'll be 3 times n, which is negative 2, so that gives me negative 6. Y to the negative 2 minus 1 is negative 3. And then don't forget to multiply by dy dx. Equals the derivative of 2x cubed will be 6x squared. I only have one term containing dy dx, and we have lots of negatives here. I'm going to move this to the other side because that's the term that contains my unknown, and I like it to be positive. So I will have negative 8x to the negative 3 minus 6x squared equals 6y to the negative 3 dy dx. Now I can isolate dy dx by dividing by this. y to the negative 3. Now I've isolated dy dx. I don't like those negative exponents. I can also factor out a 2 from the numerator, and then I can cancel it with a 2 from the denominator. So what I'm going to do, I'm going to do a couple of things in one step. I'll factor out a 2, and then I'll write that as negative 4, and then instead of x to the negative 3, I'll write it over x cubed. Minus, when I take a 2 out, I'm left with 3x squared. My denominator will be 2 times 3 over y cubed. So I just factored a 2 out of the numerator and the denominator, which I can then cancel. Let's clean this up. So I'm going to have negative 4 over x cubed minus 3x squared over 3 over y cubed. We don't want to leave our answer as a complex fraction, which means we have fractions in the numerator or the denominator or both. In order to simplify that, I talked about a shortcut when I talked about algebraic fractions that allows us to multiply the numerator and the denominator of this fraction by the lowest common denominator of all of those denominators. So that lowest common denominator would be x cubed, y cubed. And I haven't changed the value of my fraction if I multiply the numerator and the denominator by that. But that shortcut gets rid of all of those fractions in the numerator and the denominator. So my derivative will be equal to, when I multiply by this, remember I have to multiply each term by it. So when I multiply negative 4 over x cubed times x cubed y cubed, the x cubes will cancel and I'll be left with negative 4y cubed. Minus, when I multiply this times this, I will end up with 3x to the 5th y cubed. And in the denominator, the y cubes will cancel and I'll end up with 3x cubed. So that would be the derivative in its simplest form. So when you're doing implicit differentiation, it's not just the implicit differentiation that can cause difficulty. The algebraic simplification can also be a challenge. Let's take a look at another example. In my next example, I have a power as well as a product. So not only am I using the power rule when I've got y to the n, I'm going to be using it when I have this function to a power of n. So we're just going to go through this step by step. The outside function here is a power function, so I start off by taking the derivative, and the derivative will be n, which is 2, times the function to the n minus 1 is 1. Now I go inside the function and take the derivative of each term. The derivative of y cubed will be 3y squared, then times the derivative of y with respect to x, so dy dx, minus the derivative of 1 is 0. Now I differentiate 4x squared times y. It's a product of 4x squared times the function y. So in order to find the derivative of a product, I take the first factor, which is 4x squared, multiplied by the derivative of the second factor. The derivative of y with respect to x is dy dx. I add the second factor, which is y, times the derivative of the first factor, which will be 8x. My next step, I'm going to get rid of these grouping symbols, so I'm going to distribute 6y squared dy dx to each of these. So let's just take this 2 and multiply to the 3 and get a 6. So I'm going to now multiply that to each term. So I will get 6y to the 5th dy dx minus 6y squared dy dx. And I'm just going to write this as 8xy. Now I need to get all my dy dx terms on one side of the equation, so I'm going to move this term over by subtracting it from both sides. And then what I want to do is factor out the dy dx out of all those terms. So I'll have 6y to the 5th minus 6y squared minus 4x squared. And once it's factored out of all of those terms, now I can isolate it by dividing by this factor. So dy dx will equal 8xy divided by 6y to the 5th minus 6y squared minus 4x squared. I can factor out a 2 from the numerator and the denominator. So when I factor it out of the numerator, I'm left with 4xy. When I factor it out of the denominator, I have 3y to the 5th minus 3y squared minus 2x squared. I can cancel the factors, the common factors. So my simplified answer would be 4xy over 3y to the 5th minus 3y squared minus 2x squared. So this just gives you more examples to refer to while you're doing these on your own. It's using a combination of all the rules, and it can get very complex, but just try to follow through your rules, isolate your dy dx, and do any simplifications that you can when you do get a result. In the next video, I'm going to be talking about higher derivatives. So when you're ready, we'll see you on the next video. Take care.